And so you can easily verify with Excel, for instance, that if you plug in these parameter values, then you get the maximum of this function for x equal to 38, just as an example. But the parameters are uncertain, and let me treat uncertainty in a simplified way. Let me admit the presence of uncertainty by assuming that the parameter vector, which in this case is given by these 4 values, can assume with equal probability 3 different values. So I have 3 different parameter vectors which can occur with equal probability, and then I will show you what are these 3 parameter vectors. So there is uncertainty because A can assume 3 values, B can assume 3 values, each of one with equal probability. Let me show you what are these are the 3, sorry, 1 second. These are the 3 parameter vectors. I'm jumping forward and backward with the slides, but these are the 3 values of the parameter vectors. And one of them is, I think it is this one, the one that I previously considered. I'm not sure, but anyway, you have these 3 possible vectors, each one occurring with probability of 1/3. Equal probability means 1/3 each. Okay. So you have uncertainty. And now my question is, what is the best solution here? What is the best value of x? Of course, if you have a fixed parameter vector, you know how to identify the best value, because we already treated this case. If you have 3 parameter vectors, now you can identify 3 best values, 3. And now my question for you is, okay, which one would you choose then? Which one will you pick up? This is the question that we have to reply. You know that one of these parameter vectors will occur, but you don't know why. You don't know which one. You just know that they may occur with equal probability. So the question is, again, what is the optimal allocation? What is the optimum x value that you will choose? Okay, let's try to answer to this question by calling into play utility theory. Utility theory, you have a lot of information available on the web. Also, in Wikipedia, there is a quite large amount of information. Utility theory can be used in many technical applications. I'm just focusing now on the use of utility theory for solving this problem. Okay. First of all, what is utility? Let me make a premise. The utility of a solution, the utility of something is related to its ability to reach the target. And therefore, to find the solution that has the highest utility is our purpose. But we don't know how to quantify it. Because, you know, as I said, we have a target, taking a decision under uncertainty. And the way in which we want to reach the target is to find the solution that has the highest utility. First of all, utility is a quantity that is comprised between 0 and 1. And when it's associated to an economical benefit, like in this case, let's also assume that utility is increasing for increasing benefit. In mathematical terms, we can say that the utility of the minimum benefit is equal to 0, the utility of the maximum benefit is equal to 1, and the derivative of the utility with respect to the benefit is greater than 0. In mathematical terms, we take these assumptions now. We have to associate to each benefit value that we can take from this function the corresponding utility. Utility, in a way, is also a means to rescale between 0 and 1 whatever function, whatever benefit function you have to reach. And let's take, for instance, at the calibration problem of whatever model. You have an objective function. You may want to rescale the objective function between 0 and 1. Associating a utility to the objective function is a way for reaching this target. And the scaling can be done as you prefer, because you are free to assign each value of the benefit, each value of the objective function, your preferred utility, with the only condition given by these three statements. The minimum as utility is 0, the maximum as utility 1, and utility is increasing for increasing benefit. So now we have to associate, we have to complete this association between the benefit function and the utility. You still don't understand why, but please follow me, and then in 15 minutes you will understand why. Perfect. And in order to make this association, we have to provide a definition of utility. Of course, it is completely subjective, this kind of association, once that you satisfy these three requirements. But indeed, if we want to make it in an objective way, if you want to make it very transparent, let's try to formalize this association. And this is a difficult step of this lecture, of this process. So try to make this association formal. So let's consider that we have this objective function. We have a possible solution x, which is an integer, three possible values for the parameters, and so we have a finite set of benefit that can be achieved. And now we have to find a subjective way of associating this finite set of possible benefits to a utility. Okay, good. Now, in order to find this association, let's take this definition for utility. identify the minimum and maximum of the benefit that you can get according, again, to this benefit function and according to the possible parameter values. You can identify a minimum and a maximum. Okay? And because, as I said, you have only integer values that are possible for x, and also you have a benefit that for increasing x, at a certain point decreases. So it's very possible to identify the minimum benefit, which is not 0, because, you know, or it could be, okay, it could be 0, this doesn't matter. But in any case, x cannot be negative, so you can identify the minimum benefit and you can also identify the maximum. Okay, now let's assume that you go to a user and you ask him this question. Look, you have two possible outcomes from the decision that we take. And the two possible outcomes are either we assign you a given benefit for sure, which is between the minimum and the maximum, and you can get this benefit for sure with an assigned probability. So I can tell him, for instance, you have 60% probability of getting a given benefit for sure, or you have 40% probability to get, sorry, I didn't formulate it well, and let me say again. And yes, sorry. You are given a given benefit for sure, like 100 for sure. So here it is. Or you are given, and this benefit given for sure is between the minimum and the maximum. Okay. Or you are given the minimum benefit with the probability 1 minus p, where p is, for instance, 60%. So you have 40% probability of getting the minimum benefit and 60% probability of getting the maximum benefit. So let's suppose, to make the example clearer, that the minimum benefit is 0 and the maximum benefit is 500. You go to a user and ask him, I give you 100 for sure, or 0 with 40% probability, 500 with 60% probability. So in the first case you have a certain event, benefit 100. In the second case you have a risk. The risk is you get 0 with probability 40%, you get 500 with probability 60%. What would you choose? You ask the user. Okay, then some considerations. Of course, the choice of the user depends on the value of the benefit that you give for sure. So if you give for sure 490, of course you would choose 490. But another issue that is important in the decision of the user is the probability to get the maximum. Because if you give a very high probability of getting 500, he would prefer to take the risk because the probability of being successful is very high. So the p-value that you see here, which is generic, matters in the decision. If the probability of getting the maximum is very reduced, which means that the probability of getting 0 is very high, then the user would prefer to take the benefit for sure. Of course, there would be a p-value such that the user is, doesn't make any difference. And he says, okay, for this even benefit for sure, and this p-value, it doesn't make any difference for me. So you may say, look, I give you 100 for sure, or a probability of 70% of getting 500 and a probability of 30% of getting 0. And you may say, okay, it doesn't make any difference. And you can also understand that the judgment of the user on whether or not the two solutions are equivalent depends on the propensity or adversity to risk by the user. You may find a user that is very prudent, and then you will need a very high p-value to get to a situation where it doesn't matter one or the other solution. You could find a user that does like the risk very much, and he would prefer the risk, and therefore he would be convinced even for low p-values. I hope the example is clear. So we have three issues that come in today. What is the benefit that you assign for sure? What is the probability of winning, so getting the maximum? And propensity or adversity to risk. But in any case, you will be able to identify for this user a p-value such that he is equally satisfied with both solutions. This p-value is a value of probability, so it's value between 0 and 1. And the p-value which makes the user equally satisfied by the two solutions is defined as the utility of the given benefit for sure. So let me try to repeat. You have a set of possible values for the benefits. They vary between a minimum, which could be 0, and a maximum. It's always possible to identify a maximum. It's not infinity, the maximum, according to this benefit function. So you have a possible set of benefits. You have to associate to this each benefit a utility. In order to do that, you go to the user and you ask him, okay, the minimum is 0, the maximum is 500, let's give a utility to the benefit of 10. And then you say to the user, look, I give you 10 for sure, or 500 with a probability of 90% and 0 with a probability of 10%. Of course, you will say, oh no, I would prefer the second solution because, you know, 90% of probability of getting 500 and 10 is very low. So I don't have any doubt. And then you say, okay, now let's say that you get 10 for sure, or 500 with a probability of 1% and 0 with a probability of 99%. And then probably he would say, no, I take 10 because 1% is too reduced. Okay. And you say, okay, now let's say 10 for sure, or 500 with a probability of 10% and 0 with a probability of 90%. And you may say, doesn't matter to me. Okay, so it means that 0.9 is your utility of 10. Okay? And then you analyze each of the benefits with the user, and if you have more than one user, you could take a way for computing a compromise. So you get the opinions from each user, and then you reach a compromise between the users. What you have to assign is a utility to any benefit. Good. Now, let's consider, because you know you have to assign utilities to any benefit, and this is a long process. So let's focus on just 5 solutions for X, because the benefit, you get one benefit for each solution, and you have 3 benefit functions because you have 3 parameter vectors. So let's consider just 5 solutions. And these 5 solutions, in order to limit the number of the cases, are the 3 best solutions for each of the parameter vectors plus 2 solutions that I take by chance, randomly. Okay? So let's focus on 5 solutions again, which are the 3 best solutions for the 3 given parameter vectors plus 2 solutions by chance. I already mentioned to you what are the 3 parameter vectors. Let me show you in a graph the 3 benefit functions now. These are the three benefit functions with the three parameter vectors. So we take now the three best solutions for each of the curves that you see here, plus two solutions randomly chosen. And here are the possible solutions. And first, you have here this is 28 is the best solution according to the first parameter vector. And you see the three benefits in the row of x1, which is equal to 28. You see the three benefits computed according to the three benefit function that you get by using each parameter vector. And this is the average. And also I put there the minimum. So basically, this is the best solution according to the first parameter vector, and according to that parameter vector you get a benefit of 79.22. According to the second parameter vector, 74.97. According to the third parameter vector, 61.18. The average is 71 and the minimum is 61.18. Why I'm showing you the average and the minimum? Just because we consider two possible criteria to decide, which is the maximum of the average and the maximum of the minimum. Okay? Because why the maximum of the minimum? Because it's a safer solution. You consider the minimum benefit. It's the safer approach. Okay. Now, 38. 38 is the maximum benefit according to the second parameter vector. So you see, again, the three benefits, the average and the minimum. Perfect. 42 is the optimal solution for the third parameter vector. Again, average benefit and minimum benefit. And then I said that we set two random solutions. Indeed, it's just one. Sorry for that, because here, for brevity, I decided to just pick up one. So let's pick up 30, random solution. Okay? And let me compute the benefit for each of the parameter vectors, the average and the minimum. Again. Perfect. Now, if we choose the maximum of the average benefit, what would you choose? 72.26. So the fourth solution, which doesn't correspond to any of the optimal solution for the given benefit functions, would be chosen because it gives the maximum average. And if you look at the maximum of the minimum, what is the best solution? Would be the third one, 63 times 53. Okay, these are two possible solutions. Just consider that, taking the average benefit is not exactly the same than taking the average parameter values. You could also decide at the beginning to take the average parameter value and find the optimal solution there. It's your choice, it's your call. In this case, it was decided for the sake of providing an example to take these two criteria as baseline. Okay, now let's call utility into play. Just remember that the three parameter vectors have equal probability. Okay, first of all, as I said, we have to consider all these benefits. These are all possible benefits. And we have to assign utility to all of them. And assigning a utility is a process that is complicated. You have to go to the users and you have to make a proper evaluation. Now, let me make a very quick association. And by just respecting that the minimum benefit as utility 0, the maximum 1, and utility is increasing, using. And if I do that, sorry, 1 second, here. Let's just take this utility function, okay? So the utility is varying between, it's given here in tabular form, and here you see the graph. The utility is varying from 0 to 1, and you see that the minimum benefit is 61. It's the minimum because we considered only 4 solutions for x. And the maximum is 79.22. And here is the graph. And this is just arbitrary, you know, you can change it. But now we have the utilities. So my question for you is, what is the solution, given this utility graph, what is the solution among the 4 that we considered before that has the maximum utility? This is very simple. Let's show another table, because this is what now we have to do. We have to find the solution between these 4 here. I go back to the previous slide. Here, this is fine. Between the 4 possible solutions for x are 28, 38, 42, and 30. Because we consider just these 4. We have to find the one among those 4 that has the maximum utility. Okay, let's see how we can do that. So, basically, let's consider the solution 28. Okay? The solution 28 gives a benefit of 79.22 with probability 1/3. Okay, because let me go back 1 step and look at the table, at the previous table. I go back 2 steps here. You see, solution 28 has 3 possible benefits. Each of them has a probability of 1/3. Okay, and these benefits have the utility, keep them in mind, 79.22, 74.97, 61.18. Keep them in mind and look at the utilities here. 79.22 has a utility of 1. And then we had the 74.97, utility 0.6. And the other one was 61.18, if I well remember, which is 0. Okay? So let me now move forward 1 slide. So we have 79.22 with probability 1/3, it has a utility 1. 74.97 with probability 1/3 has a utility of 0.6. 61.18 with probability 1/3 utility 0. And therefore, if you want to compute the average utility, you get 1/3 times 1 plus 1/3 times 0.6 plus 1/3 times 0. The average utility is 0.53. Perfect. Now we can do the same for the other 3 solutions. And the result is not given, but let's compute it. So, I'm sorry, I wanted to go back here. So basically we have 28, x equal to 28, 38, 42, and 30. And the benefits are, I'm just copying, 79.22, and I leave a space here because I want to put the utility here, okay? So 74 97, and the third one is 71.79. Yes, second 66 times 26, and then 76, sorry, 85, and then 63.41. Third, 73.83, and then 76.63. Third one is 63.53, and then the final one is 79.11, and then we have 75.73, 61.93. Perfect. These are the possible benefits. And now I want to write here below each of them the utility. Yes, I think it's correct.
The one right. The right one, third.
Yeah, correct. It's 61, I think. Good, thank you. Now, utility. So, this is 0. Let me just try to do this. So this is 0. And then 74.97, 4.6. And this is 1.0. 76, 4.8. 4.9. And here we have 4.1. Okay, now 4.55. 4.85. And then 4.15. And then 4.95, 4.7, and here 4.05. Okay, and now average utility, and it is 0.53 for the first because we already computed it. And now here we have 1.8, this should be 0.6 because it is 0.1 plus 0.9, which is 1 plus 0.8 is 1.8 divided by 3, 0.6, if I'm not wrong. And now here is 1.55, which means 1.517. And here we have 1.7 divided by 3, which means 1.57, something like this. Let me make a computation, a correct computation. It's yes, it should be 567. And this should be the resulting average utilities. I just computed my memory, but I think I was not wrong. So the maximum U is this one. Yeah.
May I ask you how you will go to
I just said that it was just a random choice, just subjective, with the only constraints of meeting the three requirements: minimum benefit utility 0, maximum benefit utility 1, increasing utility for increasing benefit. But now I'm discussing this because the next question is how the result changes if you change the utility function. So this is the next question. And in particular, I mentioned to you that the utility function allows us to take into account propensity or adversity to risk. So how these are accounted for? Okay, perfect. First of all, you see that we could have a utility function, let's take the extremes, that rapidly converges to 1, which means that, you give a very high utility even to low benefits, or the opposite is a utility function that very slowly converges to 1. So you give a high utility only to high benefits. What is the effect on the results? If you make an experiment, you would see